Sure. All right. My apologies about starting late. I ended up only needing 15 minutes, but that's probably better than undershooting. So my apologies. I feel like I've been running around all morning, and I guess I have, but here we are, ready to do some math. Oh, feels good. Okay. Because it was just on Tuesday that we met, I'm not going to do too much of a review. We'll kind of jump into, as I say that, I'll do a little bit of, but not really. I'll just say what we covered, right? We covered things like, well, now I have to flip back through to remember what we actually said, what we talked about. We talked about real numbers and their properties. Oops. And their properties, right? So things like the associative properties or the commutative properties. We talked about negatives, how do negatives behave, just really a refresher on just kind of math in general. We talked about the distributive property, right? And we'll talk more about the distributive property in not this section, but the next section. So don't worry, there will be more. We talked about fractions, and just the kind of rules around fractions, right? And so adding, subtracting fractions, right? We have to have that common denominator. And then if we're multiplying, then we can just multiply across, and we'll deal with some more fractions today just to kind of get into it a little bit. And then we started talking about sets, and today we're gonna keep talking about intervals. Sets and intervals. So not really a review, but just a list of things that we talked about. Okay. So we're gonna keep going with these intervals, and we talked about things like inclusive, exclusive, on a number line, right? So if you're on a number line and there's an open dot, right, that means it's exclusive of that number. So for intervals continued. Let's see here, give myself some more space. All right, so intervals continued, right? We've got, and what I'm gonna do instead of what I was doing yesterday is I'm just gonna cut and write around it. And then of course I post these on Moodle anyways. So, right, if we've got these open dots, right, that's gonna be the not inclusive, right? So the exclusive. If you've got closed dots, right, that means you're inclusive. Inclusive of the endpoints. And you can have combinations of those, right? And so the inclusive would be the less than or equal to. And then, so it just goes through a couple of combinations here. Things we didn't talk about are things like this, right? Where your interval is going to infinity. So from a to infinity, well, that's the same as saying that some x, right? And we're talking set builder notation here. And we read that as the set of x such that a is less than x, right? And so a is just less than x, so x has to be all the values that are larger than a, right? And it's not including a, so we've got that open dot at a here, over here. And then it just keeps going, and if you're going to infinity, we just indicate it with an arrow, right? And so we fill in with the arrow. Same thing, we can do the same thing for the left-hand side, right? If x is less than b, then all the x's are going to be to the left of b. Right? And then if you want to just indicate the whole set of real numbers, then we're talking about negative infinity to infinity. Often I'll even put an arrow on the left-hand side. You don't have to, but often I'll just have both the arrows going both ways just to show that it's the set of real numbers. So what if I wanted you to express the following in terms of inequalities, right? So inequalities less than, greater than, less than, equal to. So express the following in terms of inequalities. Then graph the interval. So I'm going to do 3 of them. So round brackets, -3 to 0. Square bracket 2 to 8, round bracket. Square bracket 2 to infinity, round bracket. As a quick note, right, if we're dealing with infinity, it always has to be a round bracket. Oh, got crazy sunny in here. Can't really see my screen, that's okay. So, but I can see the chat still, so it's good. So if we're dealing with infinity, we always use a round bracket because infinity is not really a number, right? And so I don't want you thinking that infinity is a number. It's more of a state of mind, let's call it. Which is more funny if you're at UBCO because their slogan is a place of mind or something. Anyways, infinity is not a number. So we must always use round brackets around infinity, right? On either end. So we must always use round brackets, right? Because if infinity is not a number, then we can't go to that number exactly because it's not a thing. So that's why we have to use round brackets around infinity, right? Or negative infinity, right? And you can see that in the list above, right? Whenever there's infinity appearing, there's round brackets, right, around them. Okay, so in terms of inequalities, right, let's get fancy. Let's do some set builder notation, right? So set builder notation along with our inequalities. So I only asked for inequalities, so inequalities, I'll add it in with set builder notation. So what does that look like? Well, it's the set of all x's. So just, that's going to be pretty general, right? We always just start with, okay, so it's any x that satisfies this criteria. So it's an x such that, and then x has to be between -3 and 0, but exclusive on both ends, right? So such that, and I'm going to put x in the middle, x can be between -3 and 0, and that's it. And then on the number line, right, if I've got my real number line here, I'm going to throw down -3 here, 0 here, doesn't really matter. And on both of these, I'm going to have, oh, I'll use a different color just to show. I'm going to have open circles, and I'm talking about any region between the two. Okay. So let's practice that set builder notation with the next one again, right? So now we're inclusive of 2, but exclusive of 8. So we have to keep that in mind. So again, it's going to be the set of all x's such that, and x is going to be between two numbers, right? X has to be greater than or equal to, or 2 is less than or equal to x, right? So the equal, less than or equal to, that's the same as the square bracket. And then x has to be less than 8 and just less than because it's not inclusive. How about the number line for this guy? Looks very similar, right? We'll start here, do our real number line, and then I'm gonna plop down 2 and 8. Doesn't actually matter, spacing or anything. But what I need to show is that it's inclusive of 2, but exclusive of 8, and all the values in between. So, oh, color. How about this next one? So it's a square bracket around the 2, right? So it has to be inclusive of 2, and then it's going all the way up to infinity, right? So if we're thinking in terms of this kind of layout, right? So it's going to look the same here, but instead of stopping at 8, right? We're just going to let it go to infinity. So what we can actually do is we can just cut this guy out, right? And then just say that x has to be greater than or equal to 2, or if you want to read it kind of with the L to make it a little bit easier. So 2 has to be less than or equal to x, which means x has to be greater than or equal to 2, right? So those are equivalent statements. So here, we can say, okay, well, x has to be a number such that, and we'll just write the same setup again, right? X has to be greater than or equal to 2. And you can flip those around if you want to. But just because I want to see the symmetry between this previous one and this one, I just want to write them the same way. And they mean the same thing. So there. And then for our number line, right now we're just starting including 2, and then we're just going to keep going to infinity. So remember, we just do an arrow to indicate that it just keeps going. So here we go. So I'm at 2. It includes 2, and then it just keeps going and going and going. Okay. There. But then I'm here in the dark. We don't have blinds yet, so that's why, and it hasn't really been an issue. Well, it was, and I moved the desk, but anyways, it's really kind of annoying, but all right. So intervals, oh yeah, so here, so this one could be written, so or x such that x is greater than or equal to 2. Notice that the relationship between, so the big mouth is just facing the x regardless, and so it doesn't matter. So 2 is less than or equal to x, or x is greater than or equal to 2. It doesn't matter which one you do. Okay. Good. All right. So, good. Let's talk about absolute values. I'm not sure if you guys have dealt a lot with absolute values, so let's just get in there. See what it looks like. It's not that bad. Says I, right? So an absolute value, the long and short of it is, it'll just take any value and make it positive. So if it's positive, it'll just stay positive. If you've got a negative value inside the absolute value, then it'll just return the positive value. So we denote the absolute value with these vertical bars around. And so here, we use these vertical bars to denote absolute values. Okay. So one thing that's important is that, okay, well, this is a piecewise function, and we'll talk more about piecewise functions later, but this is the first one that we'll see, right? And so it says, and we haven't even talked about functions yet, but we will. So I just want to get that terminology in there. But it just says, okay, well, the absolute value of A is going to behave differently if A is positive. So if A is greater than or equal to 0, then that means it's positive, right? So if we think about on the number line here at 0, so for all these values, right, A is greater than or equal to 0. Right? So for example, we've got the value 2 somewhere here. 2 is coming up a lot. Let's switch that to 5. Right? And so over here, right, all these guys where A equal to 5, right? A can be any value in this region, including 0. It'll just stay the same, right? So the absolute value of 5 is 5. So the absolute value of 5 is 5. Okay. Oh, question, maybe? I'll mute you, Ian. There. Whereas, okay, so if we go from here, right, where A is less than 0, right, meaning A is going to be negative, so all these negative numbers, well, then we'll have something like A is negative 5, right? If we take the absolute value of negative 5, according to our function here, well, if A is less than 0, so if A is negative, then the absolute value actually just takes the negative of it, right? So it takes negative 5 and says, well, that's negative of negative 5, and I'll put negative 5 in brackets just to show, so we don't have negative, negative right next to each other. But we know from last day, and we remember just in general, right, that a negative of a negative makes a positive. So either way, we end up with the result of 5, right? So whether we take the absolute value of negative 5 or the absolute value of positive 5, we end up with 5 either way. So if you just remember taking that the absolute value just makes it positive, that's fine. But I just wanted to show you why it does that, right? So just quickly, how about I ask you to evaluate the absolute value of 100 and the absolute value, I should make these kind of a little bit taller probably, and the absolute value of negative 73. Just quickly, right? The absolute value of 100, well, 100 is positive, so it's just going to be 100. Whereas the absolute value of negative 73, nice, is just going to be 73, right? Because we drop the negative essentially, right? You don't have to go through and say, oh, I'm going to put a negative on there. You can just say, okay, I need to drop the negative. Good, 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 good. So there are some properties of the absolute value that you've got on your handout here. Whee. Okay. So the absolute value is always going to be positive, right? So because we're always just turning it into a positive number, greater than or equal to 0. So it can be 0 if you've got 0 in the absolute value. As we just saw, right, the absolute value of a is the same as the absolute value of negative a, so it doesn't matter, they're going to yield the same thing. So if we're multiplying or dividing and taking the absolute value, then we can just break those up, right? So it's one of those instances where we're allowed to break up the absolute value as long as you're multiplying or dividing, right? So from here, we can break up the absolute value if we are multiplying or dividing terms inside the absolute value. Okay. And then not so much to use the triangle inequality, but just remembering that, okay, if you're adding, then you can't actually break it up because the absolute value of a plus b is actually going to be less than or equal to the absolute value of a plus the absolute value of b. So, so you want to be careful, right? If you look at the example, right, you have negative 3 plus 5. You would deal with that first, right, which would put you at 2. And so you would have the absolute value of 2. Well, that's going to be less than the absolute value of 3, which is 3 plus 5. So 2 is less than or equal to 8, right? So you need to be careful that you're not just breaking up the absolute value if you're adding or subtracting, because they'll be different. Notice that there isn't even a rule for subtracting. We just tweak our addition a little bit, right? But that's more, so there are things that, now it's so dark in here all of a sudden, or at least on the screen. So there's going to be a lot of things that we talk about that it's more about being aware that they exist, right? So it's not about memorizing or anything like that. I'll tell you what I need you to memorize. There will be things that I need you to memorize, but a lot of these things, it's just kind of storing away and saying, okay, well, if I'm adding or subtracting in absolute values, they're not going to break out and be equivalent, right? And so, and then you can always just go back and look up what it is exactly, right? So this is one of those things that don't memorize, but just remember that it's a thing. Okay, so absolute values are used for distances a lot of the time, right? And so if we talk about the distance between 2 points on a real line, right? Even if I just asked you, hey, what's the distance between 4 and 10, right? In your mind, you're probably gonna say, okay, well, I need to take the distance from 4 to 10, and so I'm gonna take 10 minus 4, and then that's my distance, right? We need to be careful, right? Because, and that's what this is saying, right? If A is the smaller endpoint and B is the rightmost endpoint, then we take B minus A, which would be the same as 10 minus 4, and then we take the absolute value. We need to be careful if our leftmost endpoint is negative, right? So if I want the distance between -2 and 10, right? Then that's when I'm going to need to think about it a little bit, right? Because from 0 to 10, I know it's 10. And then from 0 to -2, I know I've got a distance of 2, right? But if we're talking about the distances, we're better off just using this little formula, right? Where the distance between A and B is going to be the absolute value of B minus A. And that's going to work every time, right? And so just as a little exercise, find the distance between, and I'll just move it so it's on the new page when it prints out later, between 2 and 17. We'll do -3 and 21, and 11 over 8 and -3 over 10. Hey, how rude. Fractions, come on. Well, we gotta get jiggy with it, right? So that's what I said. We didn't review how to deal with fractions, but here they are coming at us. So this is our chance to review them. Okay. So the first one, right, is, well, the first two are not bad, right? We already kind of talked through them. And so we've got the distance between 2 and 17, oops, by that formula is the absolute value of 17 minus 2, which is 15. The distance between -3 and 21 is the absolute value of 21 minus -3. Well, 21 minus -3 is going to be 21 plus 3, putting me at 24, which is positive. And so I've already taken, or I don't need to drop the negative or anything. The next one, right, is a little bit more involved, right? And so we want to do, I'll just move it over here so we've got a little bit more room. So the distance between 11 over 8 to -3 over 10, oh, I guess I should switcheroo these. Why am I saying that? Because one's negative and one's positive, right? And so I should have them. It actually doesn't matter, but I'm going to switcheroo these. Since one is negative, so what we're doing is we're finding the distance between -3 over 10 to 11 over 8. Because you want to think about that number line, right? You want to have, and like I said, we'll check it, but it doesn't actually matter. But you want to have the smallest number on the left and the largest number on the right so that you've got the proper interval. So this is going to be the absolute value, and I'll do big absolute value signs so that I can deal with my fractions properly. And so I'm going to have from 11 over 8 minus, so it's from b minus a, so minus negative 3 over 10. Okay. This is the same as adding two fractions, so I will simplify in there first. 11 over 8 plus 3 over 10. To combine these, right, I don't have a common denominator yet. And so we're going to use that trick that I showed you the other day. And of course, there are more elegant ways to do it, but this works every time, right? So over here, we're going to multiply by 1, right? And so we take the 10 from over here and multiply by 10 over 10. And then we take the 8 from over here and we multiply by 8 over 8 to get that common denominator of 8 times 10. And that's going to be the easiest way to do it. So we've got 11 over 8 times 10 over 10 plus 3 over 10 times 8 over 8. So now, make sure you keep that absolute value sign going all the way down. So a lot of the time it's going to feel tedious, but you don't want to forget about the absolute value sign later on. So we've got 11 times 10, because now we're multiplying fractions, right? So we multiply across. So 11 times 10 is 110, and then over 80, plus 3 times 8, 24 over 80. Now I've got that common denominator, which I just use as my denominator in my addition. So now I have 110 plus 24, putting me up the absolute value of 134 over 80. 134 over 80, I'll just check it to make sure it doesn't equal a number. No, simplifies to 67 over 40, but I'm just going to leave it as 134 over 80. Because that's positive, the absolute value of it is just 134 over 80. I'll do or 67 over 40, but you don't have to do that, right? But if you do 134 over 80, if you have this calculator or even the other Casio one, and it's set to give you the exact answers, it will give you the simplified answer. Let's see here. If you just plug it in. So it's not that bad, but I would just leave it as 134 over 80. Good, 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 good. Any questions so far? Okay. So I'll start on a new page. Right. Oops, not 12. 1.2, or for us, we'll just call it 0.2. We're in chapter 0, let's call it, because chapter 1 is functions for us. But we're going to talk about exponents and radicals, which are just roots. let's have a little refresher. How exponents and exponential notation works, but hopefully it's all good, right? And so if you've got the same thing multiplied over and over and over again, right? So let's say 5 times, then you would have that as our base, right? So then the thing being multiplied is our base, and then we raise it to the power or the exponent. So exponent or power, if you prefer. We should call it exponent, but sometimes I just like to call it the power, so just open to both, right? Because we do talk about the nth power, and then we call n the exponent, so they're interchangeable. But, right, so if we've got something like 6 times 6 times 6 times 6 times 6, right? So here, the base is 6, right? 6 is being multiplied over and over again. And then 1, 2, 3, 4, 5, right? The power is 5. So we rewrite this as 6 to the power of 5. Right? So hopefully that's ringing some bells. Just some little fun facts, right? I'll do it in pink. Anything to the power of 0, as long as it's not 0 to the power of 0, 0 to the power of 0 is 0. But any number except 0 to the power of 0 is 1. Okay. So that's something to keep in mind, right? If we've got something to the power of 0, then that's just 1, right? And just like when we multiply by 1 or convenient values of 1, like 8 over 8, for example, this is going to come in handy as well, right? If you have something that you can make to the power of 0, turning it into 1, then that can be kind of useful sometimes, right? Another thing about exponents is we can use exponents to write fractions, right? And so we can use a negative exponent to indicate that that base is actually in the denominator. Right? So here, we can use a negative exponent to indicate that a value is in the denominator, right? Showing off all our terminology from last day, right? The denominator is the bottom part of a fraction. And so we can rewrite, and I like to think of it as putting that denominator on the same level as the numerator, right? So it's a way for us to bring things up from a fraction and just writing everything on the same line, right? And so, but in order to do that, right, we need to know laws of exponents. And so here we go. Here are the laws of exponents. Should make it even bigger. There. I'll need you to be very well versed in the laws of exponents, and we will do a couple of examples here. And so we'll talk through them, and we'll see where it gets us. Okay, so we're going to be talking about the bases and the exponents, or the powers. And so first thing we need to remember is that, okay, as long as I have the same base, right, I can combine these two values, right, by adding the exponents, okay, if I'm multiplying the bases, right? If I'm dividing the bases, well, that's the same as subtracting the exponents. And I want to show you why. So a to the power of m over a to the power of n, using the rule, so this first rule, right, that I can rewrite a to the power of n as a to the negative n, right? So this is going to be the same as a to the power of m times a to the power of negative n, right? Well, so now I have the same base being multiplied, right? And so I can add these two. So this becomes a to the power of m plus negative n. But that's the same as m minus n. So that's why we get to a to the power of m minus n. Right? So that's how it evolves, right? And a lot of these will fall from that. Law number 3 says that, okay, well, I can separate. So if I'm multiplying in the power in the exponent, then I can break them up with brackets, and it won't be affected, right? So I can have a to the power of m to the power of n. That's the same as a to the power of m times n, right? So if the exponents are being multiplied, then they can just stay multiplied, and we can separate them with brackets and it won't matter. Same thing if we've got two different bases, right? So now we've got a and b as our base, and then they're both to the power of n, right? So they're multiplying inside, and we've got the power of n. So then we're allowed to break up that power onto both a and b, right? But it's important that you do it on both, and not just the b, for example. Same rule applies for division, right? You've got a over b in the inside, and then on the outside you've got to the power of n. Well, I'm allowed to distribute this n onto both a and b, right? So I have to talk about both of them. It has to get distributed on both of them, but I'm allowed to do that. Same thing, right? Even if the power is negative, it does flip things, right? Because you have a to the negative n on top and b to the negative n on the bottom. You can kind of play around with it. But, well, actually, let's do that one. Oh, I might need more room. Actually, I know I'll need more room. So 6 says that you have a over b to the negative n. And it's just a good exercise to go through this one and deal with these fractions again. So from law number 5, I know I'm allowed to distribute n. Okay, so I've got a to the negative n over b to the negative n. Fine. I know I can rewrite a to the negative n as 1 over a to the negative n. So what I'm going to do here is I've got 1 over a to the negative n. Oh, sorry. Drop the negative now, because that's what I did when I did the 1 over. Right? One thing you probably noticed is that I I try my best, and I always, well, I'll always stack my equal signs, and I want you to get in the habit of doing the same thing. So just always try to stack your equal signs. I know it wastes paper and whatever, but I'd rather just have you stack your equal signs whenever you can. There are some instances where I just kind of tack on another equal sign like this, for example, at the end maybe, if it's obvious. But as I'm working through kind of logically, I want you to stack your equal signs and really start to stack your equal signs so that you can kind of read it like a series of events. That was just a side note, but it's good. It's a good note. So you have 1 over a to the power of n in the numerator, right? So now we're going to end up with a fraction over a fraction. So then I have 1 over b to the power of n in the denominator. I know how to deal with a fraction over a fraction, right? I have to flip and multiply. And so then I get 1 over a to the power of n times b to the power of n over 1, right? Multiplying two fractions, I can just multiply across. So I get b to the power of n over a to the power of n, which is what that law says, right? So instead of memorizing that this becomes this, right, I would probably just go through and do this every time, because it's just going to be, I think it's easier than memorizing it. I just want to kind of go through and do it. The less I have to memorize, the better, right? So if you just are comfortable moving through these steps, that's way more valuable than just memorizing. Okay. Similar idea, right? If you have a to the negative n over b to the negative m, so now I've got a different power, but it does behave the same way in the end, right? And so you can even do it with different powers. You can manipulate it the same way, right? You would rewrite this as 1 over a to the n, and then over 1 over b to the m. And maybe go through and do that one on your own and make sure that you've kind of got the mechanics, and that you end up at b to the power of m over a to the power of n. Okay? But we'll leave that one, leave it to the reader, as the textbooks always say. We leave that to the reader. Okay, so I had a couple of examples prepared here. Yeah. So just as a quick, because we need to work with some numbers, it's going to be a lot of variables too. Right, so let's start with something kind of easy. W to the negative 2 times W to the negative 4 times W to the 5. Now, all these rules apply even with multiples, so it doesn't have to just be 2 bases. It can be 3, 4, 5 bases. Okay? So in this case, right, because I want to check, okay, do I have the same base? Yes, I do. Great. And then, so if I'm combining these bases, because they're the same, then I'm going to go ahead and add the powers. So I get negative 2 plus negative 4 plus 5. Negative 2 plus negative 4 puts me in negative 6 plus 5, putting me at W to the negative 1, which I can rewrite as 1 over W. W to the power of 1 is just W, so I'm just going to write 1 over W. Now I've kind of lost, I'll write down this example, the next one. Actually, the next two. Y to the power of 7 times y to the power of 0 over y to the power of 10. And I just want you to rewrite it, just simplify. And then the next one I want you to do is 8 times a to the 3 b to the negative 4 over 2 times a to the negative 5 b to the 5. Okay. And then because I had to leave my Zoom screen. Okay, back. Give you a little bit of time to work on these. I'm gonna tuck that away for later. So if you're simplifying these things, right, you're trying to just collect all your like bases and simplify the exponents. So for this little guy, right, they're all the same base, so that's something that I'm gonna just check immediately. And then what I'm gonna do is I'm gonna write these on the same level, right? And so what I'm gonna do is I'm gonna bring up the y to the 10 from the denominator to the numerator by making that power of 10 negative, right? So I can rewrite this as y to the 7 times y to the 0. Now, you could have simplified those first and then brought the other one up. The order doesn't matter here. Times y to the negative 10. Okay. Now this looks a lot like the one we just did, right? And so now I've got y to the power of 7 plus 0 plus negative 10. Dog just woke up. Don't worry, she's back to sleep now. She likes the drone of my voice. And she knows I'm here, but just kind of not talking to her. Quick side note, right? Y to the power of 0 is just 1, so you could have just ignored it. I don't think it's easier to ignore it, so that's why I kept it in there, but you could have easily done that. So now you've got 7 plus 0 minus 10, putting you at y to the negative 3, which I would rewrite as 1 over y to the 3, but either way, they're equivalent. Yeah. How about this next one? I'm gonna drag it down. Or maybe this side here. Scoot this over. So if we're doing this next one, right, I'm scanning and I see that I have 2 different bases. I've also got some numbers in there, right? So I'm gonna have to deal with that. But I can deal with those numbers separately because I'm just multiplying across here, multiplying and dividing. I'm allowed to just deal with things individually. So the 8 divided by 2, I can just do separately. Right? In fact, it might be easier to rewrite this as 8 over 2 times a to the 3, b to the negative 4. B to the negative 4 over a to the negative 5, b to the 5. Oops. Because remember, just like we can so easily multiply fractions, right? We can separate them and that's still allowed, right? Hopefully when you look at this, you can convince yourself that, oh, okay, yeah, that is equivalent to what I just did here. So you always want to check in with yourself and make sure hey, does this make sense, right? If I go back, if I go from here, can I get back to where I started? Yes, I can. So what I did was equivalent. So hence I can still use my equal sign. Right. So then I can deal with 8 over 2 just kind of on its own, right? That I can simplify to 4. And then what I'm going to do is I'm going to just write the denominator. I'm going to put it to the negative power, right? And bring it up top. So I get, I'll write the numerator out as it is. So a to the power of 3, b to the negative 4 times a to the negative 5, right? Because whatever the power is, I have to put it to the negative in order to bring it upstairs. So I've got a to the negative 5 and b to the negative 5. And there are lots of different ways that you could have done this, right? So there's a couple of different paths that you can take, but at the end, we should all end up at the same number. So if you've taken a different route, totally fine. Like you could have collected your A's together, your B's together, dealt with them individually, because you have to have the same base, right? But I've just decided to kind of lump things together. So what I've got, but now I'm going to collect my like bases, right? And so I'm going to show it off here. A to the power of 3 times a to the power of negative 5 is 5. There. And then I've got b to the negative 4 times b to the negative 5. So what I have, right, I can collect these bases. Okay. So I get 4 to the times a to the power of 3 plus 5. Wait, what happened there? There are like little hot zones down here, and sometimes my hand, I guess, goes on there, and we've got b to the negative 4 plus negative 5. So what you should have is you should have 4 times a to the power of 3 plus 5 is 8, and then times b to the negative 4 plus negative 5, putting me at negative 9. But to avoid having these negative powers, what you can write, you can rewrite it. You don't have to, but you can take it the extra step and say that's the same as 4a to the power of 8 over b to the power of 9, right? And then when I move it down to the denominator, that's when it loses that negative. Okay. Are you able to show the same but not bring the bottom up? So do you mean just like a different way of doing it? I mean, in theory, you could, okay, cool. In theory, you could bring these guys down, right? You could bring the numerator down. To me, it's just kind of easier if you just bring everything up. Let me see, how would I do it if I didn't bring the bottom up? Well, in my mind, if something, so once you've done enough of these, right, you just know that, okay, if you've got the same base up here and down here in the denominator, then you would just do 3 minus negative 5, and then you would have a to the power of 8. How else would I do it? Can I do it without bringing it up? Not really. Not for me, easily at least. The negative 8, How do you have -8? Oh, because then, so if you've got a to the 3 over a to the -5, then I just know that it's going to be a to the 3 minus -5, which would be the a to the 8. So it wouldn't be -8. Oh, nice. So all is good. Good. Awesome. Thank you for checking and asking. Okay, so for you guys, these exponents are a big player in scientific notation, which hopefully you've kind of dealt with in the past, but if you haven't, it's just a way of dealing with either really small numbers or really large numbers, right? So if you're talking, you know, amounts of water, really large numbers. If you're talking about maybe some particles in the water, really small amounts, right? And so either way, you're going to be dealing with scientific notation. So let's see here. Let's grab the thingy. Okay. So we use scientific notation. We use scientific notation if we are dealing with either really small or really large numbers. If we are dealing with really small or large numbers. Oops. Okay. So if you have something like, I don't know, 1.6 million, right? You can rewrite that as in scientific notation. And so what we do is we say, okay, well, I'm going to rewrite it and I'm just going to lob off. So I just have the first kind of actual number that appears and then rewrite it as a decimal with all the decimal places that I need. And then I go times 10 to the power of n, and then that's going to bump me out either to a really large number or to a really small number, right? If n is negative, then you're moving to a really small number, right? So if you have x is a times 10 to the n, right? A must be between 1 and 9, right? So you can't have 0.14 because that should be just 1.4 in scientific notation, and then you'd have to deal with that extra decimal move in the 10 times to the power of whatever. A must be between, must be between 1 and 9. Okay. And n, if n is positive, we are, we have a large number. We have a large number. And if n is negative, right, so negative n, I should say. That just makes more sense to talk about it this way. If n is negative, we have a small number. Okay. Meaning the decimal moves, the decimal moves left. And here, just gonna add that as a note. The decimal moves right. Okay. So, and there are rules for adding and subtracting different scientific notations, and maybe we'll come back to it, but I'm not going to be too picky about it. And last year when I talked to kind of Allison and Frank and everyone, I asked them, well, how picky are you about your scientific notation? And they'll know what they need to know is all they said. So, so that's good. So we're not going to get into the nitty gritty of the rules because they're a little bit tricky. So let's see here. I had some examples here. Well, let's start small here. Sure, use a space. If we have x is equal to 3,000, for example, right, then we can rewrite that in scientific notation. So what you do is you take kind of this imaginary decimal here and boom, boom, boom. Because remember, we want to have a between 1 and 9, right? And so what we do is we say, okay, well, that's the same as x is 3.0, or just 3 because it doesn't matter. 3.0 times 10 to the power of, and then how many times we moved here? So 1, 2, 3. 10 to the power of 3. Where this 1, 2, 3 is what's playing here. So it's how many times the decimal moved, right? And so that's why, I mean, if n is positive, so here 3 is positive, right? Which means that the decimal from 3.0 would move to the right 3 places. Okay? Whereas on the other end, if we have x is 0.000149 in scientific notation, right? I need my a, my kind of actual number to be between 1 and 9. So that's going to be this guy here, right? I want my new decimal, so I want to move my decimal to be just after the 1. So from here, I want to move 1, 2, 3, 4. 1, 2, 3, 4 in the negative direction, right? In terms of how the decimal moves. So then I have x is 1.49 times 10 to the negative 4. And that's where that comes from. Okay. So now what I said here, if n is negative here, right, then I have to move the decimal to the left. So from 1.49, I have to go 1, 2, 3, 4. And then I'll have a 0 in front of that, right? So just remember, it's how the decimal moves. Do I have? Okay, I want you to try on your calculator. Let's let, and it might not be small enough, but if we do, so try if x is 9.999 times 10 to the negative 9, I want you to try to rewrite that just as a decimal. Well, if I have 9.9999, maybe too many nines there, times 10 to the negative 9, so many nines, then this decimal here has to move 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So what that's going to look like is like this. So it equals 0 point, and then sometimes I'll just do as many zeros as I think and then just make sure, right? And so I need 1, 2, 3, 4, 5, 6, 7, 8, and then I'm pretty sure we go to the 9999. But I'm just going to make sure, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And it moves that decimal to where I expect it to be. Right? So here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So however you want to do it, just remember that a negative power is just a really, really small number, and then a positive power is a really, really large number. Oops. On your calculator, try something like, just to get a feel for how your calculator behaves, try 100 to the power of 25. Okay. So if you don't know where the power button is, that's okay. It's going to be, so there should be an X to the power of button, right? So an X to the blank power or something. So how you have to do it on this one and that other one that's from the bookstore, 100 and then that X to the power button, and it should just jump up, right? So it should just show there to the power of 25. So when I do it, it gives me scientific notation. I don't know if it's, can't tell. So it gives me 1 times 10 to the power of 50. So, so sometimes it'll give you the scientific notation. So on mine, I get 1 times 10 to the power of 50, but I know some calculators, well, some can't handle it. So some calculators show 1E50 to mean that same thing, or even just 1 with a space of 50. And so that's why I'm getting you to check it to see how yours behaves, because this one is kind of be careful if this is what yours works like. So just check your calculator and see how it behaves, because I think either the proper scientific notation, that's great. If you get the E, okay, fine. You just need to know that that's 1 times 10 to the power of 50, okay? It's just if you have a calculator that says 1 with a space, a very subtle space, and then 50 is supposed to be 1 times 10 to the power of 50, you need to be aware of what that looks like, right? And so that's why I wanted you to check it out. Okay. So let's just, before we go, let's just talk about the nth root. So getting into radicals here. So the nth root, right? We're very used to talking about the square root probably. The square root is just n equals 2, right? Or the second root. So here, square root is really just the second root. So square root. Okay. But we can take any root. And so what we do is we write the nth root inside the hook, right? So we've got the kind of the hook of the root, and I can say, well, then so I can take the 14th root of a. If it's equal to b, then that's the same as saying, well, b to the power of 14 must be a. Another way that's kind of easier to think about is, and you might have used that trick in high school, is if you're taking, say, the 14th root, right, on your calculator, what you're going to do is you're actually just going to take a to the power of 1 over 14. Okay. And so to take the nth root, and well, I can't remember if there's a, no, it's just a square root button. Okay, so that's good. So to take the nth root on your calculator, we use the fact, and it'll come up later, but the nth root of a is going to be the same as a to the power of 1 over n. Okay? And so if we have to take the 14th root of 3, that's going to be on your calculator, right? How we're going to solve this is you're going to take 3 to the 1 over 14. Which on your calculator, 3 to the power, so you've got that power button, right? And then just make sure that the whole 1 over 14 is in the power when you enter it. So 1 divided by 14, it should all just stay up top there, right? If it doesn't, you'll have to put brackets around it, or if your screen doesn't show you what it's entering, then definitely put brackets around the 1 over 14. But then we get is approximately equal to, right, because I'm just doing a decimal here, 1.08163334. Okay. So that's kind of the trick of the trade for nth roots. Okay, so I know I'm out of time. I want you to read through at least the rest of 1.2 so we can kind of go through it a little bit quicker. Rationalizing the denominator, it's pretty nasty to read, but it's going to be just another one of those things that we just need to know exists. So I'll do an example, but it's more about knowing that it exists. So if you're reading through that, then don't worry. And then if you read the fundamentals part 2 that I posted, that will be good for next day. Okay, so we didn't get as far as I was hoping, but might be because I was late. Anyways, any questions? Have a good weekend, Owen. All right, then everyone have a good weekend. Catch you on the flip side. Stop this.